All right, I'm back. All right, let's continue on with what we're doing here. I looked at the test results, and yeah, most people did all right, but there were many people who didn't do all right. And I also looked at how many people took advantage of the extra credit, which was awarded if you took the test the day, up to the day before it was due, and only half the class did it. So I don't know. And there was a very strong correlation between the people who didn't do it and the people who didn't do so well. So what Matt made me think about was that there were a bunch of people who hadn't done anything pretty much until the day of the test. So I don't know. I think there's a lesson there somewhere. All right, let's get on to test 2 here. And just a reminder, I'd like everybody to have their video on, please. Lauren, thank you. So we're looking at module 7. Oops. Okay, thanks, Lauren. It's possible you might have sent me an email. I haven't checked my emails before the class. So. But if you didn't send me an email, it's best if you do send me an email before the class, if that's going to happen. Okay, we're looking at module 7, which is all about moles. Not a particularly difficult module. And it's really like module 3, I think, except that there's very many fewer conversions to worry about. So the first thing, I'm going to not worry so much about the background here. So 1 mole is equal to 6.022 times 10 to the 23 particles. Now, the particles can be molecules if we're talking about a compound, or atoms if we're talking about an element. It's pretty easy to tell the difference between a compound and an element. An element will just be by itself as a single atom, and a compound will be a combination of 2 atoms. It could be 2 of the same atom as well, possibly, but that's what we're looking at. Either molecules for a compound, atoms for an element. That's going to be important later. This also equals the molecular weight in grams of a compound, and it also equals 22.414 liters of a gas at STP. So those are the main conversions we'll be using. I'll leave them up here so you can see the relationships between them. So when we're figuring out molecular weights, all we're really doing is looking at a periodic table and figuring out how many of each atom we have and then adding those molecular weights together. I think you're all familiar with that process. The significant figures are going to be determined by the periodic chart that you're using, and it's always going to go by the number of places past the decimal because it's an addition problem. So usually if you're told to find the molecular weight of something, somebody needs to mute, please. If you're looking to find the molecular weight of something, you'll be told what periodic table to use, or you'll be given the masses of the individual elements in the question. This is because individual periodic tables tend to vary in the numbers that they have for the molecular weights or the atomic weights. The atomic weights are formed on the basis of isotopic abundance. And as people find more and more different deposits of different isotopes in different places, then these values can tend to change from periodic table to periodic table. Not very much, but it's enough to make it off so that you could possibly get the wrong answer if you're using the wrong periodic table, if you were being asked to get a molecular weight. I think I changed the questions in this Module 7 quiz that involved molecular weight to make sure that they included the actual masses of the elements so that you didn't have to worry about what periodic table you were using in order to get the answer to that. Does anybody have any questions about finding molecular weights? Actually, let me take that back. There was one question here I had one look at, and that was the molecular weight of a hydrate. Now, these are something you're dealing with in lab right now. So if you've got CuSO4.5H2O, that's a hydrate, and hydrates are basically compounds that have water molecules around them. So copper sulfate .5H2O is CuSO4 with 5 molecules of water around it. And if you wanted to find the molecular weight of CuSO4.5H2O, you find the mass of CuSO4, which happens to be 159.54 grams, and then you add the molecular weight of 5 molecules of water to that. So that'd be 5 times 18.02. So this is something you're dealing with in lab right now. Does anybody have any question? Okay. So we start off here with something that's kind of elementary, and that has to do with turning molecules into atoms. If you've got 3 molecules of P2O5, we could turn this into a fairly elementary problem by just writing down 5 molecules of P2O5, and then we could add all the oxygens together and you see it comes out to 15. But we don't usually do that. We do it by dimensional analysis, and that's how I'm going to approach all of these problems. So it's 3 molecules of P2O5, and it is important here not just to include the unit, but also to include the compound as well, where it's necessary, times, and it's going to be didn't put enough room here. Let's try that. There we go. Molecules of P2O5 go on the bottom to cancel. And what we're looking for is atoms of O. So we're looking for some sort of relationship between atoms of oxygen and molecules of P2O5. And if we look at it, we'll see we have 5 atoms of O for every 1 molecule. So whenever you've got a line like this in between 2 units and numbers, I always like to kind of say that line as for every, because it's an equality relationship. There's 5 atoms of O for every 1 molecule of P2O5. Does anybody have any questions? So the answer comes out to be 15 atoms of O. Since the 5 is a counting number, so is the 3, then this is not subject to significant figures. Does anybody have any questions? Okay. Now, what if we wanted to extend that out to moles to atoms? Well, we could try that. We could you can look above here. You can see there's no, there's nothing that can take us from a compound to an element directly. Yeah, so we start out with 5.0 moles of AlF3, and what we're going to have to do first is get some molecules of AlF3 so that we can get to atoms of F at the end. So the moles of AlF3 will cancel. We need molecules first. And if we look above there, you can see that the relationship is 6.022 times 10 to the 23 over 1 mole, and that's times. And then we need atoms of F, and that's from molecules of AlF3. See, there was no way that we could go directly to atoms of F here. We had to go through the molecules of AlF3 to get to there. So it's 3 atoms of F, 1 molecule of AlF3. And that comes up with the answer, which comes out to be 9.0 times 10 to the 24th atoms of F. So we're looking at pretty big numbers here when we're talking about moles. Does anybody have any questions so far? Well, the next few examples are somewhat easier. We're looking at how many grams of P2O5 are in 3.10 moles of P2O5. For this one, we can go directly to grams. So it's going to be moles of P2O5 on the bottom to cancel. And we're looking at grams of P2O5. We actually do have a relationship to work with here, and that would be the molecular weight, which I've already figured up here as being 141.94 grams. And that's for 1 mole. So 141.94 grams of P2O5 for every 1 mole of P2O5. That's how to read that. And then that comes out with your answer, which is going to be 3 significant figures here. 440 dot grams of P2O5 would be the answer. So generally speaking, when we're dealing with significant figures for these problems, it's pretty much going to be whatever you start with is going to give you, there's one exception to that, but for most of them, 90% of them, whatever you start with will tell you how many sig figs to have in the answer. Does anybody have any questions? So I'm just mainly trying to focus on the setup here. So grams to moles, it's a similar process, except now it's going to be kind of reversed. So 5.0 grams of ZNO. We know it's grams of ZNO on the bottom to cancel. You notice I continue to use units and compounds, and we're looking for moles of ZNO. And 1 mole of ZNO for every 81.36 grams of ZNO, so that's the molecular weight there. So the answer is going to come out to be 2 significant figures. It's going to be 0.061 moles of ZNO. So just remember that leading zeros are not significant. Even if there's a decimal point in the number, leading zeros are never significant. Does anybody have any questions?
Yeah.
Yeah.
How do zeros not significant?
Why are the zeros not significant? Because because they're out the front. I could actually express this another way. I could express this as 6.1 times 10 to the negative 2. That way the zeros aren't even there, so they can't be significant if I can express that a different way using exponents.
Thank you.
If I had 0.0610, that zero is significant. It's a trailing 0 though. It's after the numbers.
Thank you.
You're welcome. Okay. We can also apply that to liters as well. So we've got 5.00 moles of O3. And we're interested in liters of a gas at STP, so liters of O3 goes on top. That's what we want. Moles of O3 goes on the bottom. We do have a relationship between this. We've got 22.414 liters of O3 over 1 mole of O3. And again, we end up with 3 significant figures in our answer. And it would be 112 liters of O3. Does anybody have any questions? Okay. Let's look at this next one here. Liters of gas at STP to grams. This one's an interesting one. This could be done in one step. It could be done in 2 steps as well, but if you're told that you need to do it in 1 step, this is how you would do it. So if you want to go from liters of O2 and you want to go to grams of O2, we could put grams of O2 on top, liters of O2 on the bottom. There is actually a relationship between those two. Molecular weight in grams is equal to 22.414 liters. So we can put in the molecular weight of O2 on top, and 22.414 liters will go on the bottom. Then you can see we can just go ahead and do the calculation. It's going to come out to be 3 significant figures, and that's going to be 86.9 grams of O2. Does anybody have any questions? So really, and these conversions are given to you in the question, so you don't have to memorize them. So it's really nothing to memorize. It's all about the setup. Now, this one's interesting, and this is where I get into a discussion about calculators. I mean, I see students when they get into my Chem 2 class who still don't know how to put in exponents into their calculator, and I would not like that to be the situation with you all either. So I want to show you how you can use your calculator in order to make sure that you are getting the correct answers on problems, especially like these here. So for this one, this is 1 atom of iron. That's pretty small, by the way, so you're expecting a small number as an answer. So we're talking about, if you remember, I said 6.022 times 10 to the 23 particles. Fe is an element. Fe is an element. So atoms of Fe goes on the bottom here to cancel. And we're looking at grams. So grams of Fe goes on top. But we know that there's a relationship there. Molecular weight in grams is equal to this number of atoms, 6.022 times 10 to the 23. 6.022 times 10 to the 23 goes on the bottom. And the grams of Fe, 55.85, I think it is. And this comes out to be 9.274 times 10 to the negative 23 grams of Fe. So that's pretty small, which is what we expect because it's an atom we're talking about here, and atoms don't weigh very much. All right, so that's what you should get when you put it into your calculator. And I'd like you all to get out your calculator now and try that calculation and make sure that you are indeed getting it. My favorite calculator in the world is the TI-30XA because it's very easy to use, and it's very easy to find the exponent button. It's only $10 as well. If you don't have that calculator, graphing calculators are okay for this too, but
What kind of calculator was it?
TI-30XA, I'll write it on the screen here. It's like $10. $10 from Walmart, $10 from a bookstore. It's a classic. So if you don't have that calculator, or you're not happy with the one you have, that would be the one I would get. There's another one, TI-30XS, which I don't like. It's not my favorite. Right, so most calculators have an EE or an EXP button. And that's what you should be using to enter your exponent. And that's how you would enter it, 6.022, then hit the EE button, and then 23. Is anybody having any difficulty finding the EE button on their calculator?
I found it.
Okay, is there anybody who hasn't? Not sure who this is. Whoever this is, I want you to enable your video, please. Lauren's already told me she can't because she's on a computer without a video camera today, just for today. But is there anybody else? I mean, this person here, I'm not sure who it is. Is it Yasera? Might be. Whoever you are, I'd like you to enable your video, please. All right, is anybody having trouble finding the exponent button on their calculator? So you're all okay with that, huh? So you put this into your calculator and you get the correct answer, is that right?
Yeah.
All right. So looking at the sig figs, the one atom that has infinite sig figs. That's a counting number. You can't have half an atom. You can't have 1.5 atoms. So it has to be an exact number. So that's not subject to significant figures. Now the molecular weight or the atomic weight is, and so is Avogadro's numbers, 6.022 times 10 to the 23. Both of those have 4 sig figs, so that's why the answer comes out to be 4 sig figs there as well. So that's the one exception to what I was talking about earlier. Generally, you can look at the number you're given and say, well, that's how many sig figs you're going to get, but you can't really say that in this case. Does anybody have any questions? That's one of the more difficult ones. Okay. These other ones are pretty similar. This is the last one we're going to look at actually, is the grams to atoms. Then I'm going to go through what the homework looks like and what kinds of things you're going to see on the test as well. So there's no way, again, that we can go from grams straight to atoms, because there's no relationship that we have that goes from grams of a compound to atoms of an element. We can't do that directly. So we are going to have to do something in between here. And just like before, it's going to be about the molecules. I'm going to be linking this. So we know that grams of Al2S3 go on the bottom. Molecules of Al2S3 will go on top. And the relationship there is 6.022 times 10 to the 23. and the grams of Al2S3 will be the molecular weight. Now, you'll generally be given the molecular weights in these kinds of problems, so you won't have to figure them up. And 150.17 grams is what we're going to have there. We're looking for atoms of S, and we're going to find molecules, and that's going to be in molecules of Al2S3. So the relationship there is 3 atoms of sulfur and 1 molecule of Al2S3. Does anybody have any questions? All right, so the final answer there comes out to be 6.14 times 10 to the 23, which has 3 significant figures. Adds atoms of sulfur. Again, you're expecting pretty big numbers when you're looking for a number of atoms. You're expecting pretty small numbers when you're looking for the mass of an atom. Does anybody have any questions? Anybody have any questions? All right. Let's take a look. Let's take a look at the homework here. We'll look first of all at the assignment. So remember that there's videos for every single assignment problem in this quiz, every single one. So if you're having trouble with any of them, it shows you the exact setups and how they're done. So let's look at something like this one. How many carbon atoms are in 2 molecules of C12H22O11? So you've got the answer here, but you need to show the setup and what goes in each slot. So we're looking for what goes in 1 and what goes in 2. And what it's going to be is, let's see, 12 atoms of C will go on top, and on the bottom will be one molecule of C12H22O11. So that'll go on the bottom. The rest of them are unused answers, and you do have to put the 3 in each of the ones you don't use. You can't just leave them blank. And that would be the complete answer there. Does anybody have any questions about doing these?
So if we leave them on blank, is going to count as wrong?
That's correct.
Okay.
There's a video that explains this too, that's in the same folder. So I'm just showing you here so that you can see it as well.
Okay.
Okay. Let's see. Let's go back to where we were. So that's the assignment. I think you have to get 80% on that to open the practice quiz. And here's the practice quiz. It's very much the same as what you're going to see on the credit quiz. Same formatting and all that. This is what I was talking about with the molecular weight. Notice I give you the actual molecular weights here in the question, so you don't have to go hunt them down on the periodic table. And if you use those molecular weights I think you'll end up getting the correct answer. Anybody have any questions?
So for that question, are we just multiplying?
Well, adding and multiplying.
Okay.
So it'd be 2 times Fe plus 3 times carbon and 9 times oxygen.
Okay, thank you.
For this one here, it'd be 1 times Zn, 1 times plus 1 times oxygen, and then plus 2 times water. When we're doing the next kinds of problems, then it's going to be typing stuff in. So in this case, it'd be, we're looking for moles of B, so it'd be 1 mole B goes on top. You already know it's only one step because you're told it is. And you'll notice you are given the molecular weight in the actual problem, so you use that. Express it the same way. And then you come out with your answer, which will have 3 significant figures, which will be expressed as moles of B or mole B. Anybody got any questions? Well, most of you have been doing this for a while with these kinds of quizzes because I've already done this in Module 3. It was pretty much the same thing. The homework in Module 7, 8, so 7, yeah, probably 7 and 9 and 10 and 11 is a bit more time consuming than it was in the previous modules. So this is one you definitely don't want to leave these to the last minute. I know people will, but you know, they're not going to be happy if they do that. Does anybody have any questions? Okay, let's go take a look at the kinds of things you'll see on the test here. So again, there's nothing to stop you starting to go through the test now and studying the different kinds of questions as we go through them in lecture. This sample module 7 to 12 test, remember it's the same test as you'll actually be taking. So it kind of boggles my mind that there are some people who actually failed test 1. But there's only one reason they would have failed it, and that's because they didn't spend enough time studying for it. So these are the kinds of questions you're going to see. It's pretty much the same kinds of questions as you'll see in the credit quiz or the practice quiz. So this one's grams to moles. Sorry, moles to grams, I should say. This one here is liters to grams. This one here is liters to grams as well. And this one is the atoms problem, the last one we looked at. So I'll go ahead and put this one in. So 1 and 2, that would be the relationship between the grams and the molecules. So I know that it's 118.96 grams goes of SOCl2. It goes in the bottom. And we know that it's 6.022 E23 molecules. You can see that that's how I've expressed it up here. That's why I've given it to you, so you know how to express it. And then it's looking for atoms of Cl, so it's 2 atoms of Cl. And 1 molecule of SOCl2. And then you can put your answer in down here. Now, sometimes for this one, I know it's a Cl. Some people see it as Ci for some reason, even though there's no way it could be, because the molecular weight wouldn't match it, for one thing. You can see it up here. Sometimes in Arial font, the lowercase l can look like an uppercase I. But you can see here it's clearly an L when it's written in this script. So, and the molecular weight obviously belies that as well. So if, but if something like that happened, then, I could go in and change it if I was asked to, at the end of a test. And that's it for module 7 as far as what appears on the test. The first 3 questions are straight conversion questions. Could be any conversion that we've looked at, but they're all one-step problems. You'll notice you are given the periodic table and a list of elements as well. I don't know if you'll need it, but it's there for you anyway. Does anybody have any questions? Okay, let's take a look at the syllabus here and we'll see what we're supposed to be doing here. So we just got through test 1. Remember, if you did poorly on test 1, one of the tests can be replaced with the grade you get on the final. All right, where are we? Yeah, so we're in the week of 2.8 here. So we're looking at module 7 and 8 today. All right, module 8 is not incredibly difficult. This is to do with empirical formulas. Now, percent composition is defined as the mass percentage of an element in a compound. And the way we do that, the percent mass of anything in a compound is the number of atoms present multiplied by the atomic weight of that atom divided by the molecular weight of the compound. I mean, if you think of what percent is, it's always part divided by whole. So if I was asking how many, the percent of females on the call, I'd count up the number of females and divide by everybody. That would give me the percent multiplied by 100, of course. So you can see how that's applied here. If we want the percentage of hydrogen, there's 1 hydrogen in HNO3. So we multiply it by the atomic mass of hydrogen, divide by the total mass of HNO3. For oxygen, though, since there's 3 of them, we need 3 oxygens times 16, which is the atomic mass of oxygen divided by the total mass of HNO3. You can notice also that these should add up to pretty close to 100%. We can calculate a percentage of water as well, and this is something you're doing in the lab. And if you have the total mass of MgSO4.7H2O, which is the molecular weight of MgSO4 plus 7 times the molecular weight of water, we know what the molecular weight of water is as well, 18.016 grams. So you've got to make sure that what goes on the bottom here is not just the MgSO4, it's the whole thing that includes the water. And then to get the percentage, it's 7 times the water over the entire mass of MgSO4.7H2O multiplied by 100%. You'll be doing this in the lab too. Does anybody have any questions? Okay. So let's look at a typical problem. This one here involves grams, but we'll also look at ones involving percentages as well. And I like to set these up kind of like a table, because what we're interested in with empirical formula is figuring out the mole ratio of elements in the completed compound. That's all an empirical formula is. So I do 2 columns. I do Fe on one side, I'll do O on the other. We'll start out with the grams, which were given, 11.57 grams. and the oxygen is 4.43. The next thing we want to do is find the moles. And the way we do that is we divide by the atomic mass of the element that we're working with. So for the first one, 11.57 grams of Fe, and that's going to be multiplied by 1 mole of Fe over 55.85 grams of Fe. And again, that's off the periodic table. That's how I'm getting that one. And for the oxygen, 4.43 grams of O times 1 mole of O over 16.00 grams of O. And again, it's whatever's on the periodic table. Anybody have any questions about where I'm getting the moles from? If I stopped here, my formula would be but that's not very useful because these aren't whole numbers. So what I want to do is get these moles into whole numbers. And to do that, I use something that's more math than chemistry, and that's a ratio kind of approach where I want to try and get these decimals into whole numbers. And the way I do that is I divide through by the smallest of the two that are there, and that's the 0.2072. Now, if I do that, then that'll be 1, and that'll be 1.336. Now, I still haven't got a whole number yet, but I'm getting closer. So it's Fe1 O 1.336. Now, I can't just round this. What I've got to do is I've got to look at the decimal here and figure out what kind of fraction that looks like. And then I can multiply both of these by that number to get rid of the fraction. So if I look at down here, I've got these multipliers. I'll expand this out so it gets formatted properly. Now, these relationships are all relationships that you should already be aware of, and these are decimal conversions of common fractions. So 0.25 is a quarter, 0.33 is a third, 0.5 is a half, 0.66 is 2/3, 0.75 is 3/4. And if it's close to 0.2, 0.4, 0.6, 0.8, then you can multiply by 5, because that would be like 1/5, or 2/5, or 3/5, or whatever. This seems to cause no end of trouble for students, because I'm always getting questions. Oh, are you going to include this on the test? Do we have to memorize this? Well, I mean, I think you should already know it. I think you should already know these conversions. And if you didn't know them, you could always plug them into your calculator to find out. If you didn't know what 2/3 was, you can put 2 divided by 3 into calculator, and you can see that it comes out to be 0.66. But the point is that these numbers here have to be close to whole numbers. And at the present time, they're not. So since 0.33 is a third, we're going to multiply both of these by 3. What you do to one, you have to do to the other. So we'll multiply by 3. And that would be 3 and then 4. So now the answer comes out to be Fe3O4. Does anybody have any questions? Okay. This next example is about oxides. Now, an oxide, and we learned this back from module 6, an oxide, the definition, is a compound of something with O. And that's really important to understand that that's what an oxide is. An oxide is not oxygen by itself. That's the whole point. If I was saying oxygen by itself, I would have said oxygen. Oxide is a compound that includes oxygen. That's all. So if I'm told that 1.40 grams of nitrogen is reacted to form 3.80 grams of oxide, then what I'm doing is I'm taking nitrogen, adding oxygen to it, and getting an oxide which weighs that number of grams. So when I'm doing the table here, the nitrogen mass is given 1.40 grams, but the oxygen mass is going to be the difference. It's going to be 3.80 minus 1.40 grams, which comes out to be 2.40 grams to get the oxygen. Okay. So it's not 3.80. Does anybody have any questions? So then we find the moles, and we do that by dividing by each atomic mass. 0.0995 and 0.150. It doesn't really matter how many sig figs you use here, because at the end you're only interested in whole numbers anyway. We divide through by the smallest. And that's going to be 1 and 1.501. And then if we wanted to, somebody needs to mute here. And if we wanted to make this a whole number, then we multiply everything by 2, and we'll get 2 and 3. We're looking at 0.501, which is close to 0.5, which is a half. That's why I multiply both of those by 2. So it'd be N2O3. Does anybody have any questions? We take a similar approach when we're dealing with percentages. And when we're doing percentages, what we're assuming is that we have 100 grams of compound. If we have 100 grams of compound, then the percentages match the grams in the elements. So we can just transfer those percentages straight into grams if we make that assumption. So we do that, and you can see that in the case of Na, S, and O, we have all the percentages. The masses are the same as the percentages. The moles we calculate as we did before by dividing through by the atomic mass of each element. We divide by the smallest. In this case, that's the sulfur, 0.7888, which comes out to be 1.996, 1.000, and 3.050. And when we round those numbers, because we don't have to multiply them at all, we get Na2SO3 as our final answer. Does anybody have any questions about how we deal with percentages? It's pretty much the same as what we just did. Just one little extra step in there. Okay. Yeah, okay, let's look at true formula. So when I'm finding an empirical formula, I don't know exactly what the formula is. All I know is that's the whole number ratio. So if I had N2O3 as an empirical formula, it could be N406, or it could be N609, or it could be N8012. I don't know, because there's one piece of information I don't have, and that's the molecular weight. But if I have the molecular weight of the compound and the empirical formula, then I can actually find the true formula of the compound. So an example of that is as follows. And the compound with an empirical formula, CH2, is found to have a molecular weight of 42 grams per mole. What's the true formula? So this is the way that I like to do this problem. There's a couple of ways of doing it. I think this is the easiest way. So what we do is we take CH2 and we find the empirical weight, which is going to be 12 plus 2 times 1, which is 14. So all I've done here is found the mass of the CH2. I take that and divide it into the molecular weight. So I take the molecular weight divided by the empirical weight, which is going to be 42 grams per mole. That's what's given, divided by 14 grams per mole, which is about 3. And that means that the formula would be C3H6, because that would be 3 times CH2. That's how many CH2 units are required to get to the molecular weight. The other way of doing it is to do it by trial and error and just say, well, CH2, that weighs 14. 14, that's not the molecular weight. Let's multiply it by 2, that's 28. That's not the molecular weight. Multiply it by 3, that's 42. Oh, that's the molecular weight. C3H6 comes out to be, if you were to 36 plus 6, which is 42. So that's a good way to check to make sure that you have indeed gotten the true formula. Does anybody have any questions?
So what would be the final answer?
What would be the final answer? C3H6, the true formula.
Okay.
All right, any other questions? Okay, let's go take a look at the homework here for Module 8. So remember, you do have assignment videos for each of these, or videos for each problem in the Module 8 assignment. So if you are having trouble, you can go take a look at those. Now these are a little bit different from the Module 7 ones in that they're all multiple choice. So I've got the table here, and then you have to choose which table matches what it should be. All right, so based on what you're seeing up here, moles divided by smallest and multiplier, and the empirical formula you're already given. So you just have to find the correct answer there. All right, does anybody have any questions? All right, well, that'll be fun. And we can take a look at the practice quiz. And you can see it's pretty much just multiple choice. But it's not really easy multiple choice because there's going to be lots of choices. Be careful when you get to the oxide problems, like this one here. Make sure that you realize that the mass of the oxide is given and that you're looking to subtract that to get the mass of oxygen first before you do the problem. And the credit quiz is a lot like that as well. Does anybody have any questions? Let's take a look at what you're going to see on the test. Oh, it's extra, sorry. Wrong quiz. That's the one. So the problems that are relevant to Module 8 are questions 5, which is a percent element kind of problem, then an oxide problem, just like the one we were just talking about, and then a true formula, sorry, percentage problem, and then a true formula problem. That's it. So 5 through 8 relate to Module 8. So again, that's something you can prepare for now. You can start doing those kinds of problems to make sure you can do them when you do them on the test. I honestly don't see why anybody failed the first test. I just can't understand it. If anybody wants to talk to me about it, they're more than welcome to. But I suspect it wasn't the material that did people in. It was the fact that they waited too long to start studying or didn't study at all and just winged it. That's what I think happened for those people who failed it. But nobody should be failing any of these tests. There's just really no excuse for it. I mean, if you have a commitment to getting through this course and getting a grade, then there's no reason you shouldn't be putting some time into it. SPC credit hour guidelines state that you should be doing 6 hours of work outside of the class. That's how the class is set up. It's not set up so you can do nothing and then just pass the test. No class is set up that way. If you can do that, well, more power to you, but most of you can't and shouldn't. All right, does anybody have any questions about Module 7 and 8? All right, well, we'll leave it there for today. And have a good day, and I'll see you all on Monday.
See you Monday,
Thank you,
Professor.
Professor.
Thank you.
Have a good day.
Have a nice day.
Thank you. Have a good day, everybody.